All right, so for 28, it says that we have a 10 kilogram block that's attached to a light cord. That means we're going to ignore the mass of the cord. And an electric motor is shown above. What is the rate that the motor is doing work when pulling the block upward with an instantaneous speed of 3 meters per second and an upward acceleration of 2 meters per second squared? So the first thing we need to do is do a free body diagram. So the force going down on this is going to be the mass times the acceleration due to gravity, which is 10 kilograms. 10 kilograms times 9.8 meters per second squared, or 98 newtons. Okay, but the motor is pulling up, and so to figure out how much the motor is pulling up, we essentially have to figure out the force that's going up. Now, the other thing that I know is that, and we'll just kind of leave this as a question mark, we'll call this the force going up, right? The other thing I know is that the net force of this, so the net force of this is equal to the mass of the object times the acceleration. In other words, if I just focus on the mass of this object, which is 10 kilograms, and the acceleration of this thing, which is 2 meters per second squared, then we get the net force is equal to 20 newtons. So then the net force, or 20 newtons, is also equal to the sum of these two forces. The force going up minus 98 newtons. Well, we know that the net force is 20 newtons, so we have 20 newtons, and the force going up minus 98 newtons. So we can solve what that actual force is, okay, going up, which is 118 newtons. And so, in other words, that the force going up, and I should probably put in italics, of the motor is 118 newtons. But we need to find the rate, which is power. Okay, so we need to find the rate, which is power. Let me move my face over here, zoom this down a little bit. So power is actually the force of the motor times the velocity. Okay, and I'll explain how we justify that in a second. But the force is 118 newtons times the velocity, which is 3 meters per second. When you do the math on that, it is 354 watts. Now, the thing is the dimensional analysis. I think this is a thing that might be a challenge for some. So remember that, and I'm gonna change the color here because this is the answer, and I think they rounded it to 360 watts. So let's talk about where that comes from. okay? So over here on the side, I'm going to remember that power is equal to watts, and watts is equal to joules per second. And joules, if you, depending on what formula you use, remember that remember that work is equal to force times a distance, right? Well, we'll just do it this way. Or kinetic energy is equal to 1/2 times the mass times the velocity squared. So if we think of this in terms of dimensional analysis, it's going to be kilogram meters per second squared. I'm having some issues here with my little thing here. This should be squared. So that makes this meters per second squared, okay? So in other words, this top line would be kilogram meters squared per second squared all over seconds. In other words, power, if we do the dimensional analysis, would be kilogram meters squared, right? And then this s squared gets tossed to the bottom all over seconds cubed. So if I say that power is equal to force times velocity, remember that force is a mass times acceleration, or in terms of dimensional analysis, kilograms per meters per second squared, because the acceleration is meters per second squared. So then if I do the force, I get kilogram meters per second squared. That's just for force. And then velocity is meters per second. So if I do the math on that, I get kilogram meters squared per seconds cubed. So this is a legitimate equation that you can use. We didn't necessarily talk about that in class, but it is legit. So the final answer then is this, and make sure that you know this relationship.